Looking at vessels ranging from massive container ships to small fishing trawlers reveals a universal design choice. They are almost always painted a distinct shade of red below the waterline. To maintain its speed, a ship's engine must generate enough forward thrust to overcome two primary opposing forces: wave-making resistance and frictional resistance. This chart compares these forces for slow-moving merchant ships. While wave-making resistance is a factor, frictional resistance is the dominant force, accounting for up to 85% of the total resistance pushing back against the hull. Because of this extreme friction, maintaining a clean hydrodynamic boundary layer, the thin region of water directly touching the steel, is the most effective way to improve global shipping efficiency. The red paint serves as a highly engineered chemical matrix designed to manipulate this boundary layer, protecting the ship from drag and preventing billions of dollars in fuel waste. In 1861, engineer William Froude discovered that even when fully submerged and away from the waves, objects experience massive physical friction. Water itself is a dense, resistant medium. This diagram shows the hydrodynamic ideal, a pristine hull allowing parallel laminar flow lines to slip past the steel. But marine fouling destroys this efficiency. Organisms turn a flat plane into a rough, irregular surface that breaks laminar flow into chaotic, tumbling vortices. This roughness destroys the boundary layer, exponentially increasing skin friction. Instead of slicing through the water, the ship begins to drag the ocean with it. Overcoming this biological friction requires significantly higher engine thrust, leading to a devastating increase in both fuel consumption and greenhouse gas emissions. This image shows the severe structural holes eaten directly through timber by the teredo worm. To prevent this, early shipbuilders began physically barricading wooden hulls with metal. Builders applied thin copper plates to the hulls of sailing ships like the Cutty Sark, primarily to keep these worms from destroying the ship's frame. Sailors eventually noticed a useful side effect. The copper sheathing also significantly slowed the growth of barnacles and plants. The British Admiralty attempted to improve this system on HMS Samarang by fitting iron anodes to the hull, intending to stop the expensive copper from corroding in the saltwater. The iron acted as a sacrificial anode, preserving the copper plates with electron flow, but this halted the release of toxic ions. Without leaching ions, the hull was quickly enveloped in massive marine growth, despite the metal remaining in perfect condition. The failure of the Samarang illustrated an essential requirement for anti-fouling. A hull cannot be an inert, passive surface. It must actively release biocides into the boundary layer to survive the biological pressure of the ocean. During the Industrial Revolution, structural iron replaced wooden hulls, solving the shipworm problem but introducing a new chemical conflict. This model shows the galvanic conflict created when copper biocide is attached directly to an iron hull. In salt water, the iron acts as an anode and dissolves away to protect the copper. This reaction destroys the ship's structural integrity, making it impossible to use solid copper sheets on an iron vessel. To solve this, chemists suspended the biocide inside a protective, non-conductive liquid coating to isolate it from the iron steel. The biocide chosen was cuprous oxide. This diagram shows how the microscopic copper particles are held within the protective paint base. The raw, natural color of cuprous oxide is reddish-brown, and this specific chemical requirement is the reason modern ships continue to be painted red below the waterline. Modern anti-fouling coatings function as active delivery systems, divided into two categories: soft and hard coatings. This cross-section shows a soft or ablative coating. It is engineered to let water friction shear away the outermost layer of paint, carrying attached organisms with it. This sloughing process constantly exposes fresh biocide to the boundary layer. Hard coatings are designed differently, utilizing a durable matrix that remains physically intact on the hull. This diagram illustrates how hard coatings work. Rather than flaking away, the biocide molecules slowly leach out of a rigid, porous structure into the surrounding water. This high-angle view of a cargo ship in dry dock shows the scale of maintenance required. Every 5 years, the depleted paint and biological growth must be mechanically removed. As seen here, workers use high-pressure sprayers to effectively strip the hull. This must be done in a dry dock to prevent toxic paint flakes and heavy metals from polluting the local harbor environment. These sacrificial, highly engineered delivery mechanisms dictate the operational lifespan and fuel efficiency of the entire global shipping fleet. This macro photograph of zebra mussels highlights a critical ecological threat: invasive species hitching rides on the hulls of international ships. Transporting these non-native organisms across the globe can devastate local ecosystems, making effective anti-fouling a matter of environmental protection as much as economics. The shipping industry currently relies on the deliberate release of toxic heavy metals as a necessary trade-off to maintain hydrodynamic efficiency and prevent biological contamination. Pressure to find greener solutions has led to the development of non-toxic silicone-based paints. Silicone replaces chemical toxicity with a mechanical solution, creating an incredibly slick, non-stick surface that organisms struggle to grip. While organisms might settle while stationary, hydrodynamic friction simply rips them off the slick, non-stick surface once the vessel reaches cruising speed. Until these alternatives are universally adopted, the red waterline remains the physical boundary where fluid dynamics, chemistry, and global commerce meet. This microscopic chemical layer is the only thing preventing a highly efficient logistical machine from degrading into a fuel-wasting artificial reef.